So we've looked at motion in the x dimension and we've looked at motion in the y dimension. So in the x dimension, we've looked at things that both go a constant speed and accelerated. And we've looked at things in the y dimension that you drop and they accelerate downwards because of gravity, right? So free fall. Okay, so what we're going to look at now is combining something that moves in the x and the y dimension. So for example, something like this, right? If I toss that thing, it's moving both in the x dimension and the y dimension, right? So anything that you throw and let go and gravity is the only thing that's acting on it when you let it go, that's what's called a projectile, okay? And so projectile motion is the analysis of things that you shoot or you throw or you drop that move in two dimensions. But it's easy to analyze them because those two dimensions are separate from each other. So the behavior of the object in the x dimension is going to be independent of the behavior of the object in the y direction. Okay, so let me show you a few examples of independence of motion, and then we'll come back and look at this. Okay, so what I have here is a car on a track, and the car has this ball launcher on top of it. So here's a ball, and when it passes this post, that post is going to trigger it to shoot the ball up in the air. Okay, and so what I'm going to do, obviously that's easy. If I just say what's going to happen here, it's going to shoot the ball up and land. But I'm going to push the car so that it's traveling when it shoots the ball. So it's going to look like this. Okay, my question to you is, when the ball comes back down, is the ball going to land in front of the car? Is it going to land behind the car? Or is it going to land back where it started? Okay, so pause the video, predict what you think is going to happen. Okay, so I have this loaded. Let's go ahead and try it. Here we go. I think you saw that it landed exactly back where it started in the car. So look at a slow motion copy of this. So I think you saw in the slow motion, if you look at it carefully, you can rewind it and look. When the ball went up, if you look at every point that the ball is in the air, the ball is directly above where it got shot from. So, of course, when it comes back down, it lands in there, right? Because what's happening is when I push this thing, the car and the ball are together moving at that constant velocity. So when it shoots the ball up, this motion here is independent of how it's moving this way. So I added this to it, but it doesn't change the fact that it was moving side to side. So let's look at a copy of this video if I put the camera attached to the car. So now you're moving with the car while it shoots the ball. So take a look at that. So I think in this case, you saw that when the ball shot up, it looked exactly the same as when I did this, right? It didn't even look like you were moving. The only way you could tell you were moving is because you could see the ceiling tiles going, right? Because in that moving frame of reference, you had the same velocity as the ball in the car. So if you were sitting on the car tossing something to yourself, it wouldn't be flying forwards or backwards because everything is moving with that velocity. That velocity in this dimension is independent of its velocity in this dimension. Okay, so what I've got here is a sheet of grid paper laying on a flat board on a table, right? So this board is flat. So when I put the ball there, nothing happens. So over here, there's a ramp. It's propped up, right? So that if I put a ball on the ramp, it'll roll down the ramp and I can watch it roll across the table, right? And I've defined, here's our X dimension and here's our Y dimension, okay? So if I put this thing on the ramp, I leave the board flat, right? So when I leave the ball alone, nothing happens. So if I let the ball go down this ramp, when it comes off, see how it just goes in a straight line? Right? The ball travels in a straight line at a constant velocity. Okay? So in this dimension, it's traveling at a constant velocity. So what I'm going to do now is to show you something accelerating. I'm going to prop this side of the board up. So I'm going to make this side higher by putting a piece of wood underneath it. Okay, so now this side of the board is propped up. This side's lower. So if I put a ball here and I let it go, see how it accelerates down? So when I combine these two motions, here's my Y, and here's my x. Okay, so if I put those two together, it'll look like this. So if you watch that again, it traces out a parabolic shape. So to make it a little bit easier to see, I've coated the ball with some paint. So now when I roll it down, we can see the path that the ball takes. Here we go. Right, so you see the path it takes, it makes a parabola. Here I've darkened the path a little bit with a marker so you can see it better. So I'll roll the ball again, watch. See how it follows that black line? So if I start the ball lower on the ramp, that means it'll come off the ramp slower. So see how that changes the trajectory? Now the path goes this way. If I start the ball on the ramp further up, so it's faster, like this, it travels in a wider arc, right? So this initial velocity is affecting how far it goes, but in the y direction, it's accelerating down all the time. So what I've done here is drawn how far the ball goes in equal time intervals. So in the x direction, there's no acceleration, so this ball is traveling at a constant speed. So in the x direction, velocity is just distance over time. But if you look at where the ball is in the y direction at each of these points, you get different values. So here, the ball's right there. And then right here, it's right there. And then there. So see if I keep doing this, the distance that the ball travels in the y direction is getting bigger. So if I mark these points where they're at on the y-axis, I can see how this object is moving in the y-axis. So you can see in the y dimension, these spacings are getting bigger and bigger and bigger as time goes on. Over here, in the x dimension, it was going at constant speed, so it's always 2 grid lines apart. But over here, it started about a grid line, and at the end, it's almost 2. So you can imagine if this board was propped up more, that it would have accelerated more in this direction, and these spacings would have gotten further and further and further apart, and my parabola would be more bent down. Okay, here's an example like that last one on the board where you have something that's got an initial velocity in the x, but it's also moving in the y, right? So in the example with the board, I had the board tilted up like this so that only a little bit of gravity was causing the ball to accelerate so that we could actually watch what was happening, right? So imagine you go out onto a building and you throw something. Gravity is going to make that thing accelerate down at 9.8 meters per second squared. Okay, so at all these points on here, right, as this, let's say you go out to the building and you throw a ball, right? At all these points, you have an acceleration downwards, and that acceleration is equal to the acceleration due to gravity. So the g is 9.8 meters per second squared. Okay, so we have an object moving in the x and moving in the y. So let's look at how to analyze a projectile problem. They're really not that hard. Okay, so the key thing is to break it into x and y motion. If you think about the two motions separately, they're not that hard to solve. Okay, so let's look at x first because x is easy. So in the x dimension, this thing traveled some distance this way. Right, I'll call that delta x. And I'm going to call the height that this thing fell delta y. Right? So in the x dimension, like we talked about, there's no acceleration this way. So in the x dimension, all this distance depends on is how fast you threw it initially. Just like the example with the ball, when the ball rolled slower, the parabola was tighter, and when the ball rolled faster, the parabola was wider. Same thing. So there's only one equation in the x dimension, and that's velocity is displacement divided by time. Okay? So in the x dimension, this is the only equation you need. So if you know this velocity right here, and you know the time, you could solve for the distance. In the y dimension, it gets a little bit hairier, but it's not that bad. Okay, so in the y dimension, we have something accelerating, right? So for a problem like this, the only real equation we need to look at is, if you remember our kinematics equations, we have this one. The position is a function of time. So it says that the displacement equals initial velocity times time plus 1/2 acceleration times time squared. So if we look at this motion in the y dimension, let's apply that to this equation. So first off, there's no initial y velocity. So this equation says, here's your initial velocity times time. So if I throw this thing straight in the y dimension, it doesn't have any initial velocity. So this is just going to become 0. And then I'm going to change this delta x to delta y because I'm talking about distance this way. Okay, so now I'm left with 1/2 at squared. Okay, so a, we've already said, the thing that's doing the accelerating is gravity. So I'm going to change that a to a g. So I'm left with this. So I can use this equation. If I know the time it takes for something to fall, I can use that to solve for the height. Okay, so what's similar about these two equations? Well, this one's not accelerating, this one is, right? So there's not a lot. But if you notice, they both have time in them. And that time is the same in the y dimension and in the x dimension. I mean, it has to, right? It has to be the same because this thing, if you remember breaking the motion into like this way and this way, so this ball is going to go this way to this point in the same time that the ball would if it was just dropped. And when you combine those two motions, you get a combination of the two that puts you right to here, right? So the time is the same in both dimensions. So when you're solving projectiles, you want to get the time first because that like unlocks everything. So in this equation, it's easy, right? You can just switch these two variables. But let's say you don't know this distance, you know the height. That's a really common thing. Like I have a height, but I want to know how long it's going to take to hit the ground. Well, if I rearrange this equation, there's only two variables here, right? There's height and there's time. Half is a constant and g is a constant. So if I do some algebra and solve for t, what you get is time is equal to 2, the square root of 2 times the height divided by g. Right? So this equation is useful. You don't see it on a lot of formula sheets, but it's really useful. If you have something that you start from rest, right, that's the key, that you're not starting it with any y velocity. If you have a thing and you drop it from some height or you throw it from some height or whatever, the time is directly proportional, well, not directly, but it's proportional to the height, right? So if you know the height that an object gets dropped or thrown or whatever from, you can immediately solve for the time. And then once you know the time works in both dimensions, okay? So in my y dimension, I have really two equations that I can use to help me solve. And in the x dimension, I only have one, right? Because it's not accelerating. So solving projectile problems is really pretty easy if you break it into x and y, and especially if you draw out the problem. Draw it out makes it so much easier. So to solve a projectile problem, right, kind of go over this, we have to break it into x and y, right? In the x dimension, it's not accelerating. In the y dimension, it is accelerating. So in the x dimension, where it's not accelerating, you only have this equation that applies. But in the y dimension, where it is, this one equation, for a problem like this at least, this one equation applies, and we can also rearrange it to solve for the time. So in another video, we'll look at solving simple problems like this, and then also solving things where instead of shooting it straight, we shoot like at an angle, like a mortar or a bomb or something like that. Okay?